All right, so here we go.
Mr. Kaczynski.
So, I'm sorry.
I'm sorry I'm late.
You're fine, bud. You don't need to apologize for being late. Just join the meeting and we're good to go. All right. So multiplicative recursion would also be a way to show the growth in, well, not only the decline in a cup of hot chocolate, but also the rise in the amount of mold on this piece of bread here described in this paragraph. It would also be a good way to describe the growth of COVID infections throughout the United States and the world for a time being, okay? Although that model has not necessarily continued forever and ever. So we're going to look at it with bugs today in our investigation. Bugs everywhere. Imagine that a bug population has invaded your classroom. One day you notice 16 bugs. Every day new bugs hatch, increasing the population by 50% each week. That's a key thing right there. I think we should probably highlight that. Increasing the population by 50% each week. So in the first week, the population increases by 8 bugs. So in a table like this one, we're going to record the total number of bugs at the end of each week for 4 weeks. So here we go. So there, we start off with 16 bugs, like they said right here. One day you notice 16 bugs, okay, and that's right here. And then that increase of 50% shows up as 8 bugs the first time, right? So 16 plus the 8 gives us 24. But the next time that, the next day, it's going to increase by 50% again, okay? And 50% is bigger the next time. Christian, do you have a question, or is your hand up just to tell me that you were late?
My hand's up to answer.
Oh, okay, that's fine, but I'm just going to run through it today, and so I can, I don't know, we're just kind of doing more direct instructions so that I can get you guys practicing and record this for my 5th and 6th hour, stuff like that. I know I've kind of changed my methods a little bit here, but so we're going to take half of this 12, or this 24, which is 12, which is going to get us up to 36 bugs on day 2, okay? And then the next day, we're going to take half of this 36, which is 18, and we're going to add it to that 36. Let's see, 36 plus 20 is 56. So adding 18 would be 54. And then we're going to take half of the 54, which is 27, and we'll add that 27 to the 54. So that would get us up to what, 70, 81 bugs? Okay, so there we go with 81 bugs. So the increase in the number of bugs each week is the population's rate of change per week. Calculate each rate of change and record it in the table. So this says calculate each rate of change, and we're going to record it in the table. All right. So our rate of change, so you can see here they did this first one, they did 24, which is week 1, divided by 16, which is week 0, like the start. So 24 divided by 16. So in this case, I guess we're going to do 36 divided by the week prior, which is 24. That simplifies to 3/2, or 1.5 if we write it as a decimal. Okay. Sorry if that's tiny, but again, it's 36 divided by the 24. And then the next one for week 3, we're going to take the week 3 total, 54, divide it by the week 2 total, 36. I'll show you this on a calculator too. If we do 54, let's clear that off. 54 divided by 36, there's the 1.5 again. And on this one, if we take the week 4 total of bugs, 81, and we divide that by the week 3 total of bugs, 54, let's see what 81 divided by 54 is. What do you think it is? 1.5 again. All right. Does the rate of change show a... Yeah. Does the rate of change show a linear pattern? Why or why not? Okay. to say no. Okay, it's not a linear pattern because the increase in the number of bugs, actually, yeah, let's do this in red because that's what our middle column was in. If it were linear, the increase in the number of bugs would be the same each day. So that would be 8 every single time. Okay, that would be linear as we're adding 8 bugs every single day, but we're not adding 8 bugs every day. We're adding 50% every day, and that 50% is growing up or going up every time. I might have jumped ahead a little bit on that last column, but that's okay. Let's make a graph. Let X represent the number of weeks elapsed and let Y represent the total number of bugs. Graph the data from using 0, 16 as the first point, as in week 0, 16 bugs. Connect the points with line segments and describe how the slope changes from point to point. All right. Can I scale this by ones? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, we get up to 81 bugs, so I guess I got to go by like maybe 5s here. Let's make that 10, make that 20, 30. Is this going to fit? I hope 40, 50. This will be close enough. 60. Doesn't quite get us to 80, but that's okay. And this will be week 0, week 1, 2, 4, 6, 8, and 10. So we had 0, 16. That was our starting amount, which is right about here. And then 124 is right here. 236 is right about here. 354, right about there. And 481, that's kind of up here, I guess. I'm just going to take a guess at where it is, right about there. It says to connect with line segments. Tough for me to do lines here. Describe how the slope changes from point to point. So here's what I'm going to say. The slope gets steeper from point to point. The slope gets steeper from point to point. I think I'll also graph this on my calculator just for fun here. Edit here. Let's go 0, 1, 2, 3, 4 weeks. And we had 16 bugs, 24 bugs, 36 bugs, 54 bugs, and 81 bugs. My skin's kind of crawling thinking about all the bugs. Let's go to window. We'll set our X minimum from 0 to, looks like I got it set to about 12. I'll go from 0 to, let's go to 100 so I can fit that last point in there. And if I graph it right now, I'm not going to see anything, okay, because I have to turn my stat plot on. So second Y equals enter, enter. And that turns it on. So now you can see that. I think it's more clear on the graph than mine that I hand drew. All right. Calculate the ratio of the number of bugs. Okay, so I already did this. I did it out of order, didn't I? Bink. There we go. So I think what the investigation wanted me to do was figure out these and then do 36 minus 24 is 12, 54 minus 36 is 18. So that was what I was supposed to do in step 2. But I used step 2 to figure out step 1. Like I needed to figure out 24%, half of that's 12, and then I added it. So whatever, we're kind of doing everything in a roundabout order, one way or the other. All right. Let's see, calculate the ratio of number of bugs each week to the number of bugs the previous week and record at the table. See the entry in the last column for week 1. Yeah, we did that. Repeat the process to complete your table. How do these ratios compare? How do they compare? The ratios are all the same. 1.5. This tells us that the number of bugs each week is, or how about this? Not just the number of bugs, but the total number of bugs each week is 1.5 times the previous week's total. That's what that means. So what is the constant multiplier? The constant multiplier is 1.5. If we constantly multiply the bug population by 1.5, we will get the next week. How can you use this number to calculate the population when 5 weeks has elapsed? For week 5, multiply week 4's total by 1.5. That's how we would do it. So what was week 5? It was 81, right? And if we multiply that by 1.5, we'd get 121.5. How about we say about 122 bugs? That's when it gets weird. How can you have a half a bug, right? Step 6 says multiply or model the population growth by writing a recursive rule that shows the growing number of bugs. Describe what each part of this calculator command does. Okay. Well, our recursive rule, we're going to go with 16. How about we can do this 2 different ways, okay? And maybe we should write it 2 different ways. 16, enter. I don't know if you guys, okay, well, we did recursive rules. That's kind of where we started when the Oakview people first came to me here in this class. But 16, enter. And then we're going to take that previous answer and we're going to multiply it by 1.5. And then we can hit enter as many times as we want to get that next value, okay? So in this recursive rule, 16 is the starting amount. And 1.5 is the constant multiplier. $16 is the starting amount, and 1.5 is the constant multiplier. So if we just hit 16, enter, times 1.5, and then we hit enter, we'll keep getting the bug population in those successive weeks. And there's week 5, 121.5, okay? By pressing enter a few more times, check that your recursive rule gives the sequence of values in your table. I just did that. Use the rule to find the bug population for weeks 5 through 8. Well, we just figured out 5, which is 122. Week 6, 182. I'm not going to round inside of my work though. Okay, I'll just round after I get my number. 273, that would be week 7, and 410, that would be week 8. What is the bug population after 20 weeks have elapsed, after 30 weeks elapsed? What happens in the long run? Well, I think I kind of want to write a slightly different recursive rule. One that'll keep track of the number of weeks as well as the number of bugs. So I think I'm going to do this a little different this time. and maybe you guys remember this, I'm going to start with 0, 16 and hit enter. So on my calculator, that would look like this. Second parenthesis, 0, comma, 16, second end parenthesis. That gives me the first week, or it says week 0, the first day I saw, okay? And there were 16 bugs. After that, I'm going to do this. I'm going to take answer number 1, which is the weeks, and I'm going to add 1 to that. And I'm going to take answer number 2, and I'm going to multiply that by 1.5. I think this will help me keep track of things a little bit better. So again, this time, this is our start. And this is our multiplier now, or this is our increase, our rate of change. So after 20 weeks, I'm going to type this in. I'm going to go second parenthesis, second negative sign, 1 in parentheses. I'm going to add 1 to each week, comma, second negative sign, put a 2 in parentheses. That tells the calculator the second variable that you're keeping track of. And we want to multiply the number of bugs by 1.5. And then I'll do this set notation here. And there it is. After 1 week, the population has grown to 24. 2 weeks, 36. 3 weeks, I'm trying to figure out 20 weeks. See, now I don't have to count in my head and lose track because the calculator's doing all the counting for me. I want to get to week 20. So where are you at, week 20? There it is. Woo! 20 weeks. 53,204 bugs. 30 weeks. Let's figure it out. 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. What do we got there? 3 million? Yeah. 3,068,016 bugs. What happens in the long run? What happens in the long run? Is this sustainable? Can this really go on forever like this?
No,
Or Rowan, what do you say?
Well, not realistically, but
I mean, this is what the model says, but math is one thing. How we interpret math is another, right? So I think there's going to be some problems with this. You know, I doubt my kitchen's going to have 3 million bugs. Okay, I doubt that because there's not going to be enough resources for those bugs. Okay, there's not going to be enough food for them to sustain themselves. There's not going to be enough room in my kitchen for 3 million bugs. Okay, and not to mention, I'm going to come in with the Orkin man and take care of things. Okay, so this probably isn't going to continue forever, but the model might be sustainable. You know, wait, 20 weeks? Wait, we're just doing days. No, we were doing weeks. That's right. Yeah, I was thinking we were doing weeks. So, yeah, probably not going to happen forever, but it gives us a way to measure it. And just like that, the flattening of the curve with COVID, the curve did not continue that kind of not linear path forever, right? It wasn't a curve forever. Eventually it kind of tailed off because, you know, everything, a lot of things in life grow exponentially, we call this, but it doesn't last like that forever. All right. So I think that should be enough to get you guys started. Make sure whenever you're starting the 5.1 or whenever you're starting to practice your skills, read the rest of the section that comes after the investigation too. So give those examples a good look before you get going. With that, I think we're about 23 minutes in or so. I think that's about the appropriate time for a lesson. You guys ready to go do some practice on your own? Adios. We'll see you then.
see you.
Have a
Bye.
great day. See you Tuesday.
You too.
Bye.
Bye-bye.